Welcome. Welcome to topic 10, sequences and series. This is a BC exam only topic, and I am, of course, your friendly neighborhood calculus teacher. Back once again to talk about topic 10. I don't consider topic 10 the most difficult topic. What I would say about topic 10 is it does have several difficult, extremely difficult ideas. And there are so many ideas from topic 10. You can essentially think about topic 10 as unit 10. And you'll see more often than not the series tests for convergence and divergence and multiple choice questions. You will see them occasionally in the free response. In fact, frequently they have been there. But all of that stuff, so all of those tests, you got to remember all of them. 10, 9, however many we talked about, 11, 15, who could know? So that's one thing. Another thing is anything with Taylor polynomials and Maclaurin polynomials. So writing them from the formula, writing a Maclaurin formula from something you've memorized, creating a series from one of those memorized Maclaurin series. And of course, everybody's favorite, the error bounds. So tons and tons of stuff in here. The ratio test gets used a ton when we talk about the interval of convergence. And when you're doing the interval of convergence, remember, always check to see if you converge or diverge at the endpoints. So tons and tons of stuff in topic 10. Probably one video is not enough. We'll see if I decide to record another. But regardless, here's the question we're going to start with. So this is a non-calculator question. And I'm going to assume that you have considered this, done it as best you can. Again, remember about 15 minutes a question. So if you're taking 45 minutes on a question, that's great that you figure it all out. But remember, you don't have that kind of time on the exam. So make of that what you will. Without further ado, here's my work. So for part A, we need to show that the first four non-zero terms of the Maclaurin series are x minus x squared over 2, x cubed over 3, x to the fourth over 4. So because I knew I was going out to x to the fourth over 4, when I was thinking about writing a Maclaurin series, I stopped at x to the fourth. All right, so then I went into it and I was like, okay, I need f of 0. F of 0, oh, that's spelled out for me up here. That's 0. Hey, you know what? F prime of 0 is also right here. That's 1. And then I had this formula. I'm not going to lie. That formula was super confusing for me to make sense of. Super confusing for me to make sense of. So I actually kind of did it backwards, if you will. I looked at this and I was like, okay, so this is that. So I need the second derivative, so n is 1. So if n is 1, I get the second derivative of f at 0, negative 1 times the first derivative of f at 0, which is 1. For this one, I said n was 2, because I knew that that gave me the third derivative, which is what I want here. Okay, so the third derivative, n is 2, so that's negative 2 times the second derivative of 0. The second derivative of 0 was my result of my numerator right here. That's where I got the negative 1 from. And then to get the last one over here, I said n is 3, because that gives me the fourth derivative. So that's negative 3 times the third derivative. The third derivative is what I got here, negative 2 times negative 1. So I found this formula extremely difficult to work with. Personally, it was really confusing for me. And again, the way I figured that out was I said, okay, I know that this needs to be the fourth derivative. So in order to get the fourth derivative here, n is 3. Third derivative, n is 2. Second derivative, n is 1. So that was really difficult for me. All right. So then I simplified, because again, it says show. So -1, 2 factorial, 2 divided by 3 factorial. 3 factorial is 6, 1/3. -3 times 2 is -6. 4 factorial is 24, -1/4. Then I had to figure out the nth term. So what I did here was I said that, okay, this first one right here would be like when n equals so I obviously confused myself. It worked out right, but you have options. All right. So if n is 0, and of course I forgot the x. Nice. Good job by this guy. This is again the problem with checking your own work. You know what you meant to have written. So if n is 0, -1 to the 0 gives me +1. 0 plus 1 is 1. X to the first is x. When n is 1, I get a -1 in the numerator, a 2 in the denominator, a 2 for the power of x. You could also start at 1. And if you start at 1, you'd have -1 to the n plus 1. No, -1 to the nth power. No, I was right. -1 to the n plus 1. And then this is n. We're going to infinity. I'm going to have x to the power of n. Okay. Got there eventually. Part B. Determine whether the Maclaurin series described in Part A converges absolutely or diverges or conditionally. Remember, when we're talking about absolute versus conditional convergence, what we want to do is we want to think about the absolute value of the series, see if that converges. If it does, we know it converges absolutely. If that doesn't, we consider the alternating series. And in the case of the alternating series, we'd then have convergence conditionally or divergence completely. Okay, when x is 1, the series simplifies into this, which is -1 to the n divided by n for n greater than or equal to 1. If you take the absolute value of those terms, they're all positive. You have the harmonic series, and according to the harmonic series test, the series diverges. So we consider next the alternating series. How do I know it's alternating? Because the signs go from positive to negative to positive to negative. If we didn't have that pattern, we would not be able to use the alternating series. So if it was like positive, negative, negative, that's not alternating. It's got to go one to the other and back. So to converge as an alternating series, you need to have terms as n approaches infinity that approach 0 and terms that are decreasing in magnitude. And I know that this is the case because, well, I could look at the terms here, but you could also, if you're of a mind, do some cross multiplication. Regardless, the alternating series test says that this converges, so we know that this will converge conditionally. Part C is an example of making a series from another series. So we have the series f of x or f of t. F of t just means the series f of x with t substituted in. I actually don't think it matters if you use t or x here. But we need to integrate this from 0 to x, and that is going to be the series g of x. So these are all power functions. And then I evaluated x, evaluated 0 and subtract because these all have t's in them. They're all 0 here. So I have these 4 terms. So 1/2 x squared, 1/6 x cubed. The 1/2 comes from, again, adding 1 to get 2, multiplying by a half here, adding 1 to get 3, a half times a third, adding 1 to get 4, a third times a fourth, a fifth times a fourth. So this was another really difficult one to figure out. It took me quite a while to determine the pattern here. So I went through a lot of things. So like I went through the things like, well, it's not squares, it's not a square minus. I said, okay, it's not a factorial, it's not geometric, it's not arithmetic. I was really bummed that it wasn't arithmetic because then I was like, what am I going to do? So what I did was I started thinking about here how I said this was 1 over 1 times 1 over 2. And here, this was 1 over 2 times 1 over 3. And this was 1 over 3 times 1 over 4. And this was 1 over 4 times 1 over 5. And I was like, aha. If n is 1 and 2 and 3 and 4, I've got 1, 2, 3, 4. Nice. And then this is plus 1. So that's where the n times n plus 1 came from. Again, that was very difficult for me to figure out. So if you struggled with that one, I struggled with that one. We were on the struggle bus together. Part D. Now, this was nice because they told us exactly which error bound to use. It says use the alternating series error bound to show that this is the case. Sometimes they get really disgusting and they leave this part out. And they're just like, yo, P sub n of 1/2 nth degree Taylor polynomial centered at 0, evaluated at 1/2. G is the function in part C. P sub 4 of 1/2. So what you need to do is you need to memorize, whatever you want to call it, that this kind of notation means write an error bound. So if it doesn't tell you what kind of error bound, you're kind of stuck. You're like, okay, so do I need like the Lagrange error bound, which means I need the maximum of the next derivative, or do I need the alternating series error bound where I just use the next term? How do I decide? And what it comes down to is for the Lagrange error bound, you usually have to have some pretty clear evidence statements or other information that just spells out for you, hey, so like the 6th derivative or the 5th derivative or the 7th derivative has this maximum. Or it might say that the 7th derivative on any given interval or the specific interval from 0 to 1 or like whatever is less than or equal to this. It's going to be mostly pretty clearly spelled out. The other case is that you get a function like e or sine or cosine, and then we can figure it out from there. But in this case, they tell us it's the alternating series error bound, so I know that so long as this is an alternating series that's decreasing, which I found in part B to be true, I can use this. So the next term. So what is the next term? It's the term after the 4th degree term for G. So for G, the 4th degree term is right here. So we use the 5th degree term right there. We want the absolute value of that because we don't care if we're too high or too low. We just want to know what we're in between. So if I take the absolute value of that, I get this, and this is definitely less than 500. And I did it by saying that I have 20 times 32, and the other one was 25 times 20. You don't have to do it that way, but that was what was comfy for me. Like you could definitely have multiplied this out and said that this is a bigger number than 500 in the denominator, so it's smaller. Anyway, topic 10. What a topic. What a topic. Give it up for topic 10.